We're now on example 8 in section 9.1. And this example is an exploration of what happens when the sample size increases. Everything else stays the same, but you increase your sample size. This is an investigation of that. 3 surveys were conducted to determine the proportion of Americans who believe a television set is not a necessity. In all 3 surveys, p-hat was 0.6. In the first survey, 500 Americans, so that's our sample size for this one, 500 Americans surveyed, and here's that p-hat, remember at 0.6, so 60% responded that a television set is not a necessity. Find a 95% confidence interval estimate of the proportion of Americans who believe a television set is not a necessity. So we'll use one prop, z int, x will be what? Did they give it to us? No. Remember, we said sometimes they will give us p-hat and n, but not x. So we have to find it. I'll just kind of use the margin over here and say that x equals p-hat times n. So 0.6 times 500, and we get 300. All right, so x is 300. It came out to a counting number, no decimals, so we didn't have to round it. And n is 500. And the confidence level, 95. Stat, tests, 1 prop z int, x is 300, n is 500, confidence level, 95. Lower bound, upper bound, notice the p-hat of 0.6, sample size 500. Calculator result, we'll put our lower bound 0.55706, comma 0.64294. Okay, put it in our format here. We are estimating the population proportion of Americans who believe a television set is not a necessity to be between 0.557 and 0.643. Okay, that was our first iteration of this problem. In the second survey, see, n is going to go up now to 1,000. p-hat stays at 60%. It's the same problem, and notice we're not changing the confidence level either. It's still 95%. What we need is x. X is equal to p-hat times n, 0.6 times 1,000, which of course is 600. 1 prop z int, x equals 600, n equals 1,000, confidence level does not change. So when you go back in, you have to change your x and your n, but you don't have to change the confidence level. Okay, the result this time was 0.56964. That's our lower bound. 0.63036 is our upper bound. 0.570, when I go out to 4 decimal places, that 6 says to round the 9 up, but then 9 rounds up to 10. So in other words, that 69 becomes 70. Okay, that's our new interval. Last time, we're going to increase our sample size one more time by another 500. Now it's up to 1,500. Again, p-hat, no change. Confidence level, no change. So x is equal to p-hat times n, 0.6 times 1,500, which is 900. 1 prop z int, x equals 900, N is 1500, and the confidence level is 95. Our new lower bound is 0.57521. Upper bound 0.62479. Be sure you can get these same numbers. You should run through your calculations and make sure you're doing it correctly. Okay, our lower bound 0.575. Our upper bound 0.625. Okay, now we want to do a similar analysis that we did, like we did last time. Remember, what we changed this time was sample size, not confidence level. We used the same 95% confidence level. So our first interval was from 0.557 to 0.643. And that was when N equals 500. Our next lower bound is 0.570. So that's going to be above this, maybe right here. And it stops before we get to 0.643 because it was 0.630. And that was when N was 1,000. And finally, when our N got to 1,500, we were at 0.575. And we went to 0.625. So it's visually we can see as our sample size increased and everything else stayed the same, our confidence level got smaller and smaller, more narrow, if you will. Okay, so let's write a conclusion sentence about this. As N increases, I need to spell that correctly, don't I? And this is a messy eraser. As N increases, the variability, now I know we're not seeing this number, but variability is the standard deviation, sigma, in the distribution, the variability in the distribution decreases. And remember, variability just means how spread out are your values. So as N got bigger, our values were less spread out, right? That's all we're saying there. And the confidence interval width decreases. Okay? And as we did before, let's think of this in terms of margin of error. So the margin of error is bigger for smaller samples. As we go from large to small, the margin of error gets bigger. So the margin of error is bigger for smaller samples. Okay.